that you cannot learn one other. And some of these problems require interdisciplinary things, so try to follow as much as you can. If it is aligned with your background so far, I mean, in the sense that you can follow some of this, that's great. If it is, even if it's not fully aligned, you need to make an effort. Try your best. Try your best to follow. Try your best to do, as much as you can with pen and paper. Follow those and see where you can go. And then you can also work within your war game teams and ask those of you who are more on the, let's say, whose background is more quantitative and somewhat more aligned to help explain to the others. You can do all of that. And this, a lot of it will be learning through, with everybody, cooperative, collaborative learning, a lot of it. Many of the assignments here are also designed that way. Feel free to talk to each other. If there are some specific assignments where you say this is individual, this is you have to do on your own, that's fine. But in general, there are a lot of things that you learn from each other. Okay, so as much as possible with pen and paper, or whatever device you use in lieu of pen and paper, try to follow that. If you, where is, what is that? Alright, so just give her maybe 1 second till she comes back.
So before we start, I've written very fundamental things that we are going to use. For some of you it may be simple, but if you are not dealing with math or anything, they may look very intimidating to begin with. Not this one, but some of the equations that I'm bound to write because I cannot violate physics. That's the boundary condition. But feel free to ask question now or after class, whenever you feel comfortable. From where it came, I can also refer you to more Wikipedia-like readings because they are written fairly well. I will not make it too complex, right? And also, it may be a bit overwhelming. Typically, when I teach this in my regular job setting, that is at IIT Gandhinagar, I cover this over a couple of lectures, 2 to 3 lectures. But here, since we are just trying to learn a lot of things in short amount of time, I have condensed a few. So it's totally okay that if you're finding it is too much. Yes, it is overwhelming, but we will try to get a big picture of it. That we have quantified something very important, and this indeed it was a published research article back in 1960. The derivation that we are going to do today, right? So today it may sound very trivial. What is that? You have just balanced 2 equations, but thinking about it, simplifying system, still getting a useful insight. And this actually started the concept of parameterization, which essentially gave rise to different model structure, different parameterization scheme. In fact, a lot of modeling groups of size of labs, national labs, like specialized wing of NASA or ORNL, or equivalent in India would be IITM partnerships with GFDL. So these size of labs actually are doing these parameterization, model structure development. So by no sense this understanding is trivial even for seasoned earth scientists, modelers. They start from here and then ultimately keep on adding the components. Right? But it will give you a lot of confidence. So this is it. This is how it starts, and then end is, I don't know where is the end. Perhaps nobody knows when we will understand everything about such systems. But this is certainly a good start. So Diane, you already covered that slides that you shared with us on that leadership, that group, or that lecture has not happened yet?
Not yet. Not yet.
Nothing, just start from scratch.
It's on?
Yeah, it's on.
Alright, so what we agreed to, we will assume that it's practically a simple world, zero-dimensional world. There is sun, there is earth, no atmosphere to begin with, right? And since there is no atmosphere, Right now, we are receiving 1360 watt per meter square. Per meter square is important here. Because if I multiply this by per meter square by any area, I would get total amount of energy that is available to me. Right? That's why this per meter square is important. Now, out of this 1360 watt per meter square, we already understood, again I am not representing those processes, but only 70% of it is reaching to me. I know that because all those measures were taken, and without adding any dimension, I am saying only 70% of energy is useful for me as Earth, because 31% has been reflected back in the atmosphere before it will reach the Earth's surface. Objective of this exercise is to if I pose it in form of question. What is the average temperature of Earth's surface with this very simple model? I am not saying that this is a complete description, but it's a math, it's a problem. Posed, ill posed, well posed, that will worry later. With this, can we do that? Now, if you see 1360 watt per meter square, even if we consider that Earth is a dot, right? Only one side of Earth will be facing Sun. Half of it would be not facing it, half of it will be facing it, right? So not 4 pi, so it's not a complete ball that is getting all the energy. In fact, it's a disk that would be getting that particular energy. It's a circular plate that is facing the Sun. So half side on this side, right? If you go into exact geometry, it becomes quite complex. So we will keep it very, very simple.
Since when did you become a flat earther?
So this becomes pi r square, because I said we will use radius of circle here. Pi r square multiplied by, I would not worry about this. I would only say that only 69% of this 1360 is available to me. This was watt per meter square. I multiplied it by area. Final answer would be in watt. This is the total amount of energy that my Earth, that is facing the Sun, is going to receive. So far so good. Now this applies to all the planets. Right? For Mars, this 1360 would be a different number. For Mercury, this is going to be way higher number. Right? For Venus and planets which are far away from Sun, this number will keep on decreasing, and scientists have actually established these particular relationships to see that how distance from Sun would change this number 1360. So this 1360 is for Earth, right? So for Mercury, I think it is something, I have to check that, but it's function of r square. So that number changes quadratic, inversely quadratic to the distance, so it would be square of this particular number. That's why temperatures are much higher. But yeah, we are interested in this 1362 pi r square. Now we are interested in temperature of Earth's surface. Let us refine this particular question even further, make it a bit easy on ourselves. In equilibrium. Equilibrium means temperature is not changing. Okay? Because if temperature is changing, it becomes transient state. Then we need to include specific heat capacities at what rate it is changing. Too complex for our first model. Our idea is to develop first model. So what would be condition on energy for something, for temperature not to change? What would be condition on any body for its temperature not to change?
That's zero entropy.
So entropy again would be related to that. Let's make it even simpler. So without introducing entropy, can we just talk in energy terms if possible? But answer is once like a simpler level of entropy. How entropy of system will not change. So if you have, so think of it in terms of saving. When our savings are in equilibrium, if we are spending exactly same amount that we are earning, there is no change in savings. So energy in is equal to energy out, right? So only three conditions are possible. If energy in is greater than energy out, energy in is less than energy out, and energy in is equal to energy out. There is no other mathematical relationship I can write for incoming and outgoing energy, right? So what happens if I am getting more energy than I am radiating back? What should happen to temperature? If incoming energy is greater than going out,
Increase.
temperature should increase. Yes, absolutely. What should happen for second case? Absolutely. Right? I always think it in terms of savings, money, right? E in is what I am earning, E out is what I am spending. So that difference should tell me whether my savings should increase, decrease, and so on. And this is where it should not change. Right? So this one is the easiest one. But underlying equation is same. We are modeling rate change of temperature with respect to time based on incoming and outgoing energy. Right? In full form, I will write this as a differential equation again of E in minus E out. But I don't want any such intimidation right now from differential equations. So I will focus on the last point, that E in is equal to 1. So this is our E in. So if I highlight this, this is what I will call as energy that is coming in from the sun. Because today we all agreed that yes, sun is only source of energy that is worth quantifying. Even if we have minor fluxes coming from other planets or wherever, but sun is our primary source of energy. So far so good. Let us focus on going out. Why Earth is not a source of energy, right? Just like moon is not a source of energy. It only reflects back what it receives from sun. Same with Earth. It only reflects back what reflects back in a sense that it gets that energy, part of it is reflected. We already subtracted that 31%, part of it increases its temperature, and by virtue of temperature it emits. Right? It reaches certain temperature and then it starts emitting, because an iron when heated becomes red, and that's when it starts emitting. Same happens with the earth, right? Iron doesn't have its own source of energy. It got temperature from the fire, got red, right? And then that's what it is emitting. So earth will be emitting because of its temperature, Ts. Right? If its absolute temperature is 0 Kelvin, it will not emit anything. But we know that absolute temperature of Earth is greater than absolute 0. Absolute 0 is minus 273 degrees Celsius. Right? Fairly too low. And we know that is not true. So our assumption that Ts is greater than 0 Kelvin is correct. So far so good. Now this is where we need to bring some thermodynamical equation into picture, some law into picture, and as I mentioned, Stephen-Boltzmann law comes into picture, which essentially says that whatever is E out is proportional. It depends on Ts. So higher is the temperature, more would be the energy that would be emitted out. Wonderful. But it is not just a linear relationship, but it is raised to power 4. This is a law. I am not proposing that, right? This is what Stephen Boltzmann proposed. We study in form of a law. There are so many laws that we will not be deriving, but using them as we go through the derivations. And it's a fairly well established relationship that relates long wave radiation and temperature, right? And this is important in a sense that it's T to the power 4, not T to the power 1. So and this has to be Kelvin.
So Udit, you gave the example of a flat earth and the sun when you gave this. Will it also work with my cup of coffee, T to the power 4, difference of temperature between
Yes.
the coffee and the air temperature?
Yes, absolutely. Yes.
Good assignment. How fast will the coffee cool? What happens if I put a steel spoon in the coffee? Will you change it?
We'll put it today.
Okay. We'll put it today. Good.
Yes.
He's anticipating all his qualifying exam questions.
Because by now I have started taking qualifiers. So, how do we remove this sign of proportionality? If something is proportional and I want to change it with equal to, what we do? Some constant comes into picture. So, if we said Stephen Boltzmann law, you will say that this is some Stephen Boltzmann constant, a Greek symbol. Again, we will not worry about it too much, it's a constant. Whenever y is proportional to x, we will say y is equal to mx, a constant is introduced. And this becomes Stephen Boltzmann law. We started from what was observed, wrote it mathematically, right? And we will keep it very simple, as I promised. We will assume that whatever Earth is getting, it is radiating back, and we call this as black body radiations, right? If we introduce more parameters, we make them grey body, right? In black body radiations, whatever comes, they reflect it back fully, right? So right now we'll keep it simple. Now this is E out, and that is it. I want to keep it very simple in my first iteration. This is, its unit is also per meter square. Okay. Everything here is per meter square. Now, Earth will be emitting as a sphere. It received as a circle. Why? Because only one side is facing practically its sun at one time. But under equilibrium, all points will have same temperature. So it will radiate in all directions. Right? So what is area? So if we assume that Earth is a perfect sphere, total amount of energy that it will radiate outwards becomes 4 times pi r square. It receives in one direction, emits in all directions. Receives in one direction, emits in all directions. Right? Right? Again, a very simple example is, so if that's the projector, I put my hand in front of it. This side will receive all the energy. It will start getting warmer, but over the time, my back of the palm and front of the palm will try to come in equilibrium, right? If they are in close contact, and this will be at same temperature, so my virtually entire of my hand will be radiating energy in all directions. So received in one, emitted in all, 4 pi r square comes into picture. So this also becomes part of our story. For equilibrium, we write E in is equal to E out. right? So we are essentially now writing E in was pi r square S into 0.69 is equal to 4 pi r square epsilon TS4, and that is it. I did not know radius of Earth here because both of them will cancel out, pi will cancel out. So it becomes S by 4 into 0.69 is equal to sigma Ts raised to power 4.
What is S?
Yeah. So S is the amount of energy that is coming from sun in watt per meter square. Thank you.
Yes.
This is this. Is it correct? So, to avoid confusion, let me substitute it here. 1360 by 4. This is a constant, right? Physicists established its value as 5.67 10 to the power minus 8 watt per meter square K4. Again, this is a constant that we know from physics, just like we know, right, acceleration due to gravity. We know capital G, the gravitational constant, right? I'm just showing the parallel. The way to determine it would have been different, but it's a constant in this particular discussion. The only unknown in this particular equation is T. Only unknown here is T. One equation, one variable, paradise for mathematicians, they will solve it. Right? We get Ts is equal to 1360 by 4 into 0.69 divided by 5.67 into 10 to the power minus 8 raised to power 1 by 4. This is it. Kelvin. Looks very intimidating, but you know, it's just putting two equations together. E in is equal to E out. 1 by 4 just comes by the virtue it is T to the power 4. If it was T square, we would have used T square. Right? Nothing we can do about it. If it is T4, we use it T4. We get our answer. If you solve it, right, answer would come something in range of
250, 2.6.
absolutely. That is absolutely correct. If you remove 273 from it, what is the value? So this is 253 Kelvin. In degree Celsius, what it is? Remove 273, something minus 90 degrees Celsius. If the model is correct, answer is wrong. Because we know that Earth's temperature is 15.5 degrees. But it's not a bad start at all. Why? Because I have not violated any law of physics for this beautiful, simple thing. Right? I might have made certain simplifications that take a lot of things away from this system, which is totally fine. I will start bringing them back, but I will ensure I am only adding the elements back without violating any physics. As long as I am doing that, it's not a bad model at all. Right? It's a great model to understand. Bad model to predict. I will not go with this answer, but I will add element exactly to the same model, because so far there is nothing wrong done in terms of physics. Right? Mistake would have been if I would have said I don't know how to take square root or under root power 4. I will represent it as t square. That is a fundamental mistake. Right? I have used the law established. Right? The reason I am iterating it so many times, because sometimes you overlook that that establish things and try to keep on adding elements, and then we don't know what went wrong. Now we will reflect upon what really went wrong, how to bring that back, and so on. Now there is one very beautiful thing that physicists and mathematics do quite often, that they don't want to deal with t to the power 4 and t to the p cube and so on, because it makes this system a higher order system. And the problem is we would not be able to directly relate that, if there is 1 unit change in radiation, how much would be change in temperature, just by looking at the system. Because it's t to the power 4, you have to simplify it, take 1 by 4 and so on, because the changes in t is not linearly related to s, right? So mathematicians would often tend to linearize this system. We will come to that, right? And that's where parameterization will also come into the picture. What we missed here? Why do you think our answer is off by 30 degrees Celsius? Yes.
We have the greenhouse gas effect.
We absolutely ignored atmosphere, and that was one significant component in our atmospheric processes. Now there are two ways to do that. Either we bring all the physics of greenhouse gases, all the chemistry of greenhouse gases in realistic manner, right? Or we use some mathematical formulations to represent greenhouse gases in some ad hoc manner. Now ad hoc seems to be sort of a bad word. Why ad hoc? I want to be realistic, but there is a trade-off. The moment you bring realistic, you have to bring each and every element associated with greenhouse gases without violating physics or mathematics. So, for our first level of understanding, this ad hoc understanding is not bad, right? How I will do that? I will first of all focus without greenhouse gases and try to linearize my model. What linearization means? I had Ts, right? That is my variable of interest. I know everything else. I only don't know this. Ts is nothing but temperature in degrees Celsius plus 273 that we require for conversion into Kelvin. I know this, right? I can divide and multiply by T naught. What's the problem? Divide and multiply by same number. Again, just see that how model thinking happens. Don't worry why I divided by this and so on, but how the model thinking progresses. How very simple mathematics will take us there, right? So we will write Ts is equal to Tc divided by T naught plus 1 into T naught, right? If I raise to the power 4 on both sides, I can do this. Now one thing is for sure here, that Tc is temperature in degrees Celsius. We know that answer is way less than 273. Earth's temperature is not 273 degrees Celsius for sure, right? So mathematician would immediately observe this equation and make some interesting observation that, hey, this number is always less than 1, because T naught is 273, it's fixed because it's in Kelvin. Tc is, we know answer is going to be 15 degrees Celsius, 20 degrees Celsius. Even with most of the global warming scenarios we are talking, it is going to be plus minus 3 degrees Celsius probably. So the ballpark number is there. But one thing is for sure, with 100% guarantee, that Tc upon T naught is less than 1. So it becomes some 1 plus x raised to power 4, where x is less than 1. Right? In in classes on algebra, mathematics, right? We were doing it all the time to write whatever entrance exams or equivalent stats, but I never knew where to use it. This is the first time I used it. That this would make sense here, right? Because we'll again go by the prudence of mathematicians. So they said that, if you have 1 plus x raised to power n and x is less than 1, don't hesitate to write it as 1 plus nx plus n square by 2 factorial and so on and so forth, right? And whenever this number is less than 1, you forget about these higher order terms and focus on first 2 terms. We borrowed this understanding part from physicists, part from mathematicians, and wrote it as sum 1 plus nx. Now interestingly, we started from x to the power 4, which was non-linear, which was uncomforting for us. Take these all square roots and so on, very non-intuitive thing. Right? From mathematicians, we linearize, from their understanding, we linearize this model. This 1 plus x to the power n is simply 1 plus nx. Right? 1 plus 4x. And we already know that x is equal to Tc by T naught. Right? So, we say that, come on, this is nothing but T naught by 4, 1 plus 4 times Tc by T naught. If I can assume that Earth is a dot, this assumption is not a bad assumption at all. Right? So, I know this is not a problem. 273 raised to power 4 is not a problem. It's a fixed number. This we don't know, right? T naught we know. I can always write this as Ts raised to power 4 as T naught raised to power 4 plus 4 times T naught power 4 into Tc by T naught. Right? I can always put the values here. 273 raised to power 4 plus 4 times 273 cube into Tc. Right? Rather than carrying this, I will say you are A and you are Why? Because this is just a constant, right? 273, whatever it is, it's a constant. It's not varying at all in my entire design of experiments. This is just a constant. I will say you are A, you are B. Sigma is also constant. Even if it comes, I will say, okay, you are still a constant. Na? You become A prime or A hat or still stay A, just change the value. Right? So what I end up with, that using that beauty of physics given by Stephen Boltzmann law, combining it with this binomial expansion that is very well established in world of mathematics, I have linearized my entire model into that this is 0.69 into S into pi r square is equal to 4 pi r square into epsilon into A plus B into Tc. This is the same model. Keep it even simpler. I will remove the common terms. I just end up with 4 into sigma into A plus B into Tc. It's a linear model now. It is a fairly linear model now. If I have to solve for t, I can further simplify it. I will say that this sigma is also a Greek symbol, right? Looks very intimidating, these pi, sigma, just to see that in equation makes it very difficult for us. I will just say that this is 0.69s divided by 4 equal to a prime plus b prime, because it's a constant. You multiply constant by constant, you are ending up with a constant. You call it anything. I now know, and this is my net incoming radiation, right? Because plus minus what is my incoming forcing, I can simply solve for Tc now as whatever is forcing. I will call this entire term as forcing. This is one word you will hear again and again, read again and again in IPCC reports, in book that Professor Ganguly suggested to read, Kerry Emanuel's book. Forcing. What is coming from outside is forcing on our system. So we simply say that this is forcing and minus A divided by these equations, equation that I am writing in number 2 and equation in number 1 that I am writing here, I will take from here. They are, if not same, they are identical. But you see how much simplification has happened? Yes.
A dash,
Doesn't matter. It's a constant. A dash, B dash, start with A. But it's a constant. We know the value. Let's keep it simple. Right? If you look into F minus A, these are identical equations. Answers would be different slightly, but not by hell lot of magnitude, because we never violated any maths or any physics. X was less than 1, way less than 1, this approximation works well. So, but interesting thing is here, now we know everything in that system. Right? In a sense, I can now really change F by 1 unit, and in no time I can tell you how much temperature will change, because it's a linear equation. For example, if I say that y is equal to 3x, if I change x by 1 unit, you will immediately say, hey, if it is changing by 1 unit, y will change by 3 units. Because it's a linear equation. The moment I say, y is equal to x raised to power 4 plus x cube, please change x by 1 unit, you will say, wait a minute. I can still do that, it will take some time. So that is the power of linearization. Right? So this linear models look very simple, but we have entered into inclusion of greenhouse gases in ad hoc manner. How? In that case, A and B, when we did it wrong, was determined totally mathematically. Right? Because A was a constant, 273 raised to power something, B was a constant, 273 raised to power 3 multiplied by sigma. So, scientists said that, I don't want to know enough about greenhouse gases, I am designing my first primitive model. Can I pose a different problem here, where I say that if Ts is equal to 15 degrees Celsius, if average temperature of Earth's surface is 15 degrees Celsius, initial question was, what is the, I don't want to add atmosphere, what is the value of surface temperature of the Earth? We did all the math, we got it wrong. Right? Then we agreed we have to bring in atmosphere. Then we also agreed today that atmosphere is too complex just to capture in one equation. Still we are interested to understand few implications of greenhouse gases without going into details of physics, which is needed, which we do today, but we started from somewhere. I am taking you back to 1960s when all this development happened. Right? So it is more easier problem now. you know 15 on this side and all you need to keep on changing values of A and B till you get your answer right. Right? And these A and B are called as parameters of the model. I did not know enough about a process. I still want to capture that. I will force fit a number that takes me to the reality. Far, far away from the realism, but takes me to the reality. Right? And these A and B values got revised. Just to give you an example, that the values of A and B that we get without including atmosphere, if we do not include atmosphere, we get value of A as 315 watt per meter square, we get value of B as 4.6 watt per meter square per degree Celsius, and we get surface temperature to be minus 19 degree Celsius. This totally agrees with that T to the power 4 calculation you did. For these values of A and B, average temperature of Earth's surface comes out to be minus 18 degrees Celsius. When we solved it exactly, what was the value we got? Minus 19 degrees Celsius. Right? Of course, this is an assumption. We lost 1 degree Celsius, but the change is not of the sign or a drastic magnitude that is happening here. Right? Then, when we have to bring greenhouse gases, we say that please try using value of A as 202 watt per meter square, value of B as 1.25 watt per meter square per degree Celsius, and plug into this particular equation, your TC would come out to be 15 degrees Celsius. This is parameterization. You simplified the entire system, right? You made certain mathematical expansions, right? You expanded that. You say, okay, these are the values of A and B that takes me to the reality. We have not included physics realistically, but we have not done anything wrong till this point. This was Budico 1969. Those who are working world of climate and weather, they have heard this word very frequently, Budico framework, Budico parameters. This was zero-dimensional parameterization proposed in 1969. Right? And then multiple scientists say, okay, we will not expand this particular equation like this. We will expand it in some other way. We will get different values of A and B. Right? So that becomes another parameter of the same structure. Right? The analog is I and you are interested in same goal. Right? Now let's increase the scale. You are one modeling group, I am another modeling group. Our objective is same. Let us determine fate of Earth when carbon dioxide changes. We are not talking to each other. You are working in parallel universe on the same objective. We agreed to that, we will use same boundary conditions. For us, sun will be the same object. 1362 watt per meter square is a number. Distance is same. We will not change that. We will meet after 5 years, 10 years and see what values of temperature we got. What would happen is that you will use a different model structure if we are not talking. I will use a different model structure. I will solve my mathematical equation separately. I will represent these particular equations separately. We will end up with two different models to understand same process. Because both of us do not understand enough about the process. Right? It would have been a straightforward equation, y is equal to 3x plus 4, and both of us use same values of x. Doesn't matter you meet after 1 day, 2 days, 5 years, 10 years, 20 years, we are essentially going to be the same answer because we understand everything about this simple equation. There is no randomness here. There is no lack of knowledge here. But here we don't have knowledge. We met, decided a common goal. We will meet after because we will use different parameterization to get our answers. We ended up with 2 models, right? At present, there are 35 modeling groups that work in parallel, with some collaborations of course, but for simplicity they work in parallel and they come up with their own projections. That hey, with the same sun, with same carbon dioxide 400 parts per million concentration, we will meet in a meeting and then we will convene again after 10 years and we will discuss our outputs, right? So, and they will run much more complicated models. We will just see what is under the hood. But this becomes model inter-comparison projects. They run these models in coupled mode. It becomes coupled model inter-comparison projects. So one modeling group will say that, hey, I ran the model with same boundary condition, average temperature of Earth would be 18 degrees Celsius, 3 degrees Celsius warming is expected. Second modeling group will come, hey, with same boundary conditions, average temperature would be 16.5 degrees Celsius. Third modeling group will come and say, hey, average temperature would be 19.5 degrees Celsius. Now who is wrong and who is right? So 3 people came, just like here, 2 parameters proposed, modeling the same phenomena. Who is right and who is wrong? How you will evaluate that? Perhaps none of them are right, none of them are wrong, we don't understand enough about the system. We will deal with an uncertainty that these are plausible outputs with different model structure. If you would have known model structure, if you would have known greenhouse gases, their exact role in this particular model, there would have been no uncertainty. Right? Or we will say, you are closer to reality, I will pay more weightage, I will assign more weightage to you because you are closer to 15.5 degrees Celsius. Right? But still, there is an inherent uncertainty involved in these particular predictions. Right? Now, that is about multiple models, parameterization, and we have to appreciate that even for a simple model, in 30 minutes, 20 minutes, we ended up with parameterization. So, parameterization is essential to model any complex process where we don't enough represent it fully or do not understand it fully. But despite that, what we can extract from this particular system, let us try to see. Now, from this, one thing that we notice that this is F divided by V minus A divided by. But this is a very simple equation, no atmosphere, no detailed mathematics represented here. Can I ask a meaningful question here? That if carbon dioxide doubles, for example, what would be change in temperature? Right? I can ask that and I will show how mathematically we will do that here. One thing is clear when we talk about change in carbon dioxide. That means there is change in forcing. Effective forcing is increasing. Why? Because we are not letting heat escape out. So effectively we are retaining more energy here. Right? So that means some things are changing. So what I can simply do is that if I just differentiate both sides, that rate change of temperature is dF by V, these all are constants will go away. Right? So I have essentially related temperature and carbon dioxide in more physical sense now. Because I realized that when I missed carbon dioxide, my estimates were way off. Right? So one element that you suggested, please try adding greenhouse gases and see do we get to a real answer. I said okay, I can add greenhouse gases in a very simple manner, and this is one model I am proposing. This is actually a model. When we talk about GCMs, right, GCMs would be multiple equations written at multiple locations at multiple time points, but they are mathematical expressions. So this is a model. This is a living model of a zero-dimensional Earth system process that relates F to T. Right? If you are lost somewhere, what is climate model? This is climate model. Right or wrong, that we will discuss. But this is a model. Give me F. Give me what is the forcing. I will tell you the temperature. I have related to. Right? So one thing is clear that if we measure change in dF, this is the variable, this is the boundary condition that is changing. I can go to Mauna Loa laboratory, get the records and see that how much carbon dioxide concentration has changed. And now I know a relating equation that if carbon dioxide changes by this time much, how much would be change in dT? I have essentially done the climate sensitivity analysis. If there is 1 unit change in carbon dioxide, what would be change in temperature? Now it is very linear model. Just tell me the value of B. I will just divide that particular change and tell you what is the answer. Right? Now, when we talk about forcing and carbon dioxide, right? Forcing and carbon dioxide, it involves chemistry associated with carbon dioxide. For example, if I double carbon dioxide, what would be change in forcing? Would forcing also double? Quadruple? What will happen? Right? Because carbon dioxide is trapping gases. That is what we learned today, that greenhouse gases don't let long wave emissions to go outside. But question is, let us say initially if I double the amount of carbon dioxide, how much gases will escape? So that's where chemists came into picture. They said, this relationship is not linear. Right? So they propose that whenever we talk about change in forcing, it is some 5.35 log CO2 upon CO2. What does that essentially mean? That if you double carbon dioxide, it will not just increase temperature by 2 times. It would be much slower increase, and it is a logarithmic function. This is where experimentalists come into picture. They experimentally, in different setups, keep on increasing concentration of carbon dioxide and see how much heat is getting trapped. Your car is a classic experimental setup in that particular case. Right? That, okay, how much temperature changes, I can measure concentration of carbon dioxide if I put some measuring instruments there, if I double how much temperature changes. So what it is essentially saying that change is slower, change in forcing is slower than the concentration itself. Why? Because logarithm is applying a brake. It is not that this is doubling. Right? So this is called as radiative forcing. Now when we double carbon dioxide, this number comes out to be 3.7 watt per meter square. Now understand that. What is the energy we are receiving from sun? Even if you have lost in mathematics, that is fine, you will relate to it what I am going to say here. Please pay attention. We will write, I will share my notes, so don't worry about that. How much energy we were receiving from sun? If you 1360 watt per meter square, right? We said 1/4 is effectively coming to us 300 watt per meter square. If we double carbon dioxide, change would be 3.7 watt per meter square. 1% of what we are receiving. So all the discussions of change in radiative forcing because of more greenhouse gases are essentially about 1 to 2% variation in radiative forcing than what we are receiving from the sun. If you have heard the names RCP 2.5, RCP 2.6, RCP 4.5, RCP 8.5, if not you will hear that sooner. That essentially is 2.6 here is 2.6 watt per meter square. Right? If we, for example, put brakes on our emissions, we will still, it's not like industries will drop to zero, right? Still we will be putting carbon dioxide, or we have already put enough carbon dioxide. That net radiative forcing, because of changes we have already done pre-industrial era till today, would be still 2.6 watt per meter square. The worst case scenario talks about 8.5 watt per meter square. That means if we don't agree with any accord, all countries continue industrialization, by end of 2100, we will add additional 8.5 watt per meter square of radiative forcing because of carbon dioxide. But this is the essence, that changes in carbon dioxide would result in change in forcing. But we are interested to relate forcing to temperature, right? And now we know that if pre-industrial carbon dioxide concentration was 280 ppm, CO2 in 410 ppm, you already know that we have added 3.5, 3.7, 5.5 and so on. And once I know that my model is ready to tell me that if there is 1 unit change in forcing, how much my temperature change will be. Because I already know these parameters from different experimental groups. This is the story of zero-dimensional climate model. We represented Earth and Sun by a dot. We said energy comes, energy goes away. Equation became t to the power 4, too complex. Went to mathematician, they expanded it for us. He said, tell me A and B. I find the value of A and B for right conditions. I said, these are the parameters. Right? Assuming that my model is correct, whatever are the changes, from F to DF to DT, I try to relate changes in carbon dioxide to radiative force. Now in first place, yeah.
By the way, when Udit was talking about RCPs, some of you may have heard, or we may have just briefly discussed it, but we did talk about these what-if scenarios, right, that are modeled in various ways by economists, social scientists, etc., population experts. These what-if scenarios then give us certain trajectories for potential carbon dioxide or carbon dioxide equivalent greenhouse gas emissions. These trajectories have a name. These are called RCPs. So these scenarios are called SSPs, right? Shared socio-economic pathways, and the carbon dioxide or greenhouse gas trajectories that are generated out of that, these are called RCPs, representative concentration pathways. These then act as forcing, meaning how they modulate forcing in the models, and then you get outputs from these models. Okay, and you will hear a bit more about that, where I think Dion talks about NCAR models, right, which is a very simple model, but which can help illustrate certain concepts. And I believe Shochen or Danish or both of them talk about the analysis of climate model, simulations and observations, and so at that point you'll hear more about the specifics of this. So, yeah. So basically from 0D to watt per meter square, we are essentially talking about 3.7 watt per meter square, and this particular number is not some fictitious number that comes to us. It comes from chemists, then incorporated into our models, and essentially fuels all the discussions around Paris Agreement and what violations of would lead to us, because we don't know the future, right? We can only make certain assumptions about the future. So by 2100, 8.5 watt per meter square additional radiative forcing. But the key takeaway is that it is 1% to 3% variation that we are worried about, because the time span is so short in which we are talking about these particular changes, that till 2100, what if we increase carbon dioxide concentrations to a level that it adds additional 8.5 watt per meter square, the implication for temperature would be 1.5 degrees Celsius to 2 degrees Celsius to 3 degrees Celsius. Since this model was very simple, right, we didn't have that uncertainty quantification around that variation. But when you start bringing more elements, more uncertainty will come, because so far
it was 2 dots, and we did not understand so many things about these 2 dots also. Now if we increase the complexity, more elements will come, but even with such simple model, we can answer such elegant question that how doubling of carbon dioxide will change the temperature, which was not a small feat when these models were designed, because it basically related so many things in something that matters for us. Because if you remove discussions around temperature, I keep on saying, concentration of nitrogen oxide will become this much teragram, you will say okay, fine, because until we quantify its implication for biosphere, life on earth, various elements that we are used to see that around us, we would not be able to understand its implication. So from forcing to change in temperature, that immediately started making sense, and when we put it into retrospect, how we change from n-dimensional models, where we will say that Earth has a curvature, there are multiple layers within the ocean above the atmosphere, using exactly same fundamentals, that what comes in goes out, S by 4, 1 minus alpha, now discretized at multiple time steps, multiple resolution. I can keep on refining my estimates of delta F. And these essentially becomes GCMs, where you resolve these particular processes at multiple steps, and you cannot solve. So whatever we did there, we were able to find the numbers by hand. I can write all the equations for this, but I cannot solve this particular equation, because variables cannot be separated, and I have to only approximate state of the system. So see, just from 0 to 1, complexity of mathematics increased dramatically, right? But then computers come into picture, where we discretize it, write it, and solve it. And once we have these model outputs, they give us precipitation, temperature, using very similar concepts that ultimately feed into our engineering findings, that what matters, how things are going to look like in next 50 years, 100 years, what we call as depth duration curves that are used to design storm systems and so on. And this is just beginning of fascinating world of climate, right? I know it's too much to absorb, but I hope I still made a point that complexity is at heart of these climate systems, but rather than running away from it, it has to be embraced, but starting from 0 to 1 to 2, n, and ultimately use the outputs knowing what basic terminology means. With that, I'll end my talk today, and of course I will keep on talking to you. I hope you enjoyed the discussions. Thank you.
Thank you, Udit. This was wonderful. How many of you feel that after this lecture and after listening to the videos and looking at the slides, and it's okay to share the slides, right? You can explain to, let's say, high school students this same thing, but without any Udit over here. Give me a show of hands if you feel like, yeah, I'll at least take a shot. I'll look at this video a few times again, I'll look at the slides, and if a few high school kids are interested, yeah, maybe I could do it. Or I don't know, if my uncle or granddad or who have you, right, or my aunt or grandma, if they're interested, hey, I have this cool thing to show at the Thanksgiving dinner table. Don't try that, but I'm just saying. Then you could do this in your own way. I mean, each time each of us do this, we do things in our own ways, and we have to keep the audience in mind. But with all that, how many of you feel somewhat confident that at least you can try? Show of hands. How many out of 32? Maybe 12. So, okay, Udit, you get 12 out of 30.
That is great start, I know.
All right, thank you very much.